And so there was our group assignment, so nice and easy. So from here, let's start talking about how we actually generate light. So now we talked about Maxwell-Ampere's law as well as the rest of Maxwell's equations. It turns out that electromagnetic waves are actually generated by this term in the Maxwell-Ampere law. So specifically the displacement currents. So in this case, we have the closed loop integral of the magnetic field dotted by the differential length is then equal to our mu naught epsilon naught times the integral of E dot dA. So it's this term along with Faraday's law, which says that the closed loop integral of the electric field dotted by the differential length is then equal to minus the time rate of change. And I forgot my time rate of change here. Bad professor, there we go. Integral of B dot dA. So basically, it's the interaction of these two guys which gives us light. So even though we have Gauss's law has no contribution to it, as well as the first term of Ampere's law, or Maxwell-Ampere. So it's actually the combination of these two in the fact that, again, this one says that a time-changing electric field creates a magnetic field. Simultaneously, that time-changing magnetic field creates an electric field. But because of this negative sign here and this positive sign here, what we get is actually harmonic oscillation, our favorite friends, right? And harmonic oscillation, as we talked about before, actually is what generates waves. So let's kind of talk about a concrete example of how this thing works. And one thing I'm going to point out before that is this only works if I have a non-steady state. So basically meaning that if I had stationary charges, for example, or a stationary or constant moving charges, there is no light generated. So no light generated. So it has to be true is to have a time-changing electric field, which starts the whole entire process, or a time-changing magnetic field, which starts the whole process. We have to have dynamics. So it is dynamics which leads to the generation of lights, which means that we have to have some sort of acceleration. So basically, all this thing points out to us then is we have to have acceleration. Now, instead of mathematically doing this, because I'm sure everybody's eyes would glaze over and they wouldn't pay any attention to what I'm doing anyways, not to mention it relies on some heavy Calc 3 stuff that I'm sure, at least I know most of you haven't quite had yet. So let's talk about a actual physical situation where we actually get light or electromagnetic radiation, I should say in this case. And this is actually a antenna. Let's talk about how an antenna works. So the way an antenna works is we're going to look at specifically what's called a dipole antenna, which is actually what's in your cell phone. So this is actually a dipole antenna, where in this case you have two rods, which are going to be connected together via an AC generator. Okay, so we have AC here. So whenever you see the squiggly line with a circle around it, this means alternating currents. So in this case, we have an alternating current system. So let's say initially at t is equal to 0, there is no charge on this guy or this guy. Right? So, but we're going to start to flow a current. So as time goes on, what's going to happen then is we're going to have positive charges, say, move to this side as time goes on, which means this other one then is going to be negatively charged. So I'm going to get negatively charged on this side. Now, what we know then is that we have positive charges here, negative charges here, which means what are we going to create? An electric field, right? So we're going to get positive to negative. So I'm going to create electric field lines, which are going to do this. Okay, so these are going to be my electric field lines. But since I also have current moving in, that means then we have a current moving in this direction. So I'm going to have currents moving in this direction. All right. If I have current, what else do I have? What does current generate? A magnetic field, right? So we're also going to have a magnetic field where we put our thumb in the direction of the current, curl our fingers around in the direction of the magnetic field, which means here we're going to create a magnetic field then, which points into the board in this case. You guys doing okay? So this is my magnetic field pointing into the board. So basically all this is saying then is what? As time increases, initially we start off with zero electric field and we start off with zero magnetic field. So if I plotted, in this case, my electric field as a function of time, as well as my magnetic field as a function of time, what's going to happen then is this one's going to start off at zero, and then the size of the electric field is going to increase, increase, increase until eventually it's going to reach its maximum when this thing becomes fully charged. Okay. Now, since this thing is AC, what that's going to do then eventually is switch the direction of the current, which means now the current here is going to get smaller and smaller and smaller and smaller, which means the amount of charge which is on here is going to get smaller and smaller and smaller and smaller until eventually this thing is going to become neutralized. And then all the positive charges are going to move to this side, and then the current's going to go in the opposite direction. Okay. So in this case, as that is happening, the electric field then size is going to get smaller and smaller and smaller and smaller until eventually it's going to go to zero. Now, simultaneously, the magnetic field is doing exactly the same thing. So it starts off at zero. It's then going to increase, 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 increase until the current reaches its maximum. And then the current is going to start tapering down. And then eventually it's going to go to zero at exactly the same point that the electric field goes to zero. Now, from there, what ends up happening then is once this thing becomes negatively charged and this guy becomes positively charged, the electric field is simply going to switch in the opposite direction. Okay, so now my electric field is going to go this way. My current's now going to be downward, which means my magnetic field will now be out of the board, which means that everything switches direction. So as time goes on then, this thing now is going to flip directions. So now my electric field will now point down in this direction. And then go through the whole entire process again. Simultaneously, in the magnetic field, the current's going in the opposite direction. So it's also going to increase, increase until it reaches its maximum. And then do it all over again. Which means, what are we creating? A sine wave, right? This thing then is simply going to be a sine wave. And this one is also going to be a sine wave. Go ahead.
What's on the y-axis?
Oh, magnetic field. Sorry. Did I put magnetic field here? Sorry. Backwards. So this is how we generate actually lights, right? Or in this case, radio waves. So what happens in this case then, again, is because the current is moving upward, right? We're getting more and more charge here, which means the magnetic field is increasing due to the current. My electric field then is increasing. These two are increasing in phase with each other, which basically means that's what? There is no phase difference between the two of these. So this means then that my electric field, as a function of position in time, will be the amplitude of the electric field. That shocks folks. Get rid of that one. Times then sine, this one sucks as well, but that's okay, k times x, where I'm saying x in this case is the direction at which the wave is moving, x in this direction, minus, this is a right moving wave, times omega t plus the phase vector. Simultaneously, the magnetic field will look exactly the same. So this is my amplitude, be 0 times sine of k times x minus omega t plus my phase vector. Let me put my vector sign on here. What's what? Which one? A? Okay, yeah, that's our wave number from 1,000 years ago. Guys remember the wave numbers? So this is our wave number. So one thing I should point out here is because we're dealing with waves again, all those things that we did at the beginning of the semester are coming back to haunt us. What's up? Good review for the exam, exactly. Yep.
Not be values since we're talking about different directions.
What do you mean?
Put like the lines around it, doesn't that only just mean the value?
Oh yeah, okay, I got you. Yeah, let's drop the absolute values. No, you're right. I should be proper about these things, but yes, you're absolutely right. So it should be the vector portion of that. So, everybody's doing okay? Now, in this case, what's happening then is the wave is moving outward in this direction, right? So in this case, we're moving our wave at the speed of light, moving in this direction. One thing I want to point out here is notice that at this point here, my electric field points in this direction, right? Because it's tangential to this circle. My magnetic field is into the board, which means if I put my fingers in the direction of the electric field, curl towards the direction of the magnetic field, which is this guy here, my thumb then points in the direction of the propagation direction. Okay? So in this case, I'm going to point my fingers in the direction of the electric field, curl towards the magnetic field. My thumb then points in the direction of wave propagation. Okay? So one thing to point out here, again, is that what? My E cross B then is proportional to the direction of wave propagation. Okay. So this will be something that's going to become important. So notice in this case, again, I get two waves. I get an electric field, which is moving as a wave. I get a magnetic field, which is moving as a wave. And in this case, they are in phase with each other. Okay. So this thing goes with the sine wave. This thing also goes on the sine wave. And this thing is what we call linearly polarized. So we create what's known as a linearly polarized wave. Now, this is not the only type of wave we can have. We can have also what's called a circularly polarized wave. So we can have circularly polarized. In that case, what happens is that they're 90 degrees out of phase from each other. So the electric field is 90 degrees out of phase from the B field. So what happens in this case then is it actually circles around the axis at which it is traveling. So think of basically a helix. The thing is creating a helix in this case. Now we're only going to be playing with linearly polarized light, but just note that this is actually something which is true. Okay. Now another cool thing about this is as the electric field moves outward, since the direction of the electric field and the magnetic field change directions, what ends up happening then is somewhere out here, you're getting an electric field which is pointing in this direction. But simultaneously, after that, you'll have a magnetic field, or sorry, electric field coming in this direction and points in the other direction. These two guys will superimpose on each other, which then creates these loops of a field. So what happens in this case is out here, we're going to create these kind of closed loops of electric fields, which wrap around like this. And that's what this diagram here is basically showing. So in this case, we have, again, my electric field initially is pointing this way here. Now, since it changes direction, it's pointing this way. These two guys will interact with each other by superposition, which creates these cool kind of closed loops. Now, as the wave gets further and further and further away, the size of these loops here is going to stretch out further and further and further and further until eventually we're going to get way out here where these moving waves are going to look like simply straight lines. So when it gets out here, this is what we call the far field limit, or simultaneously what's known as the radiation zone, where in this case, my spherical waves, which is this thing is creating, these spherical waves which are moving outward, get stretched so far that the radius basically goes to infinity, which means that it becomes a plane. Okay, so these guys now create what are known as plane waves. So my plane waves, again, is when the radius of curvature goes off to infinity. So these guys get stretched to basically be planes. What's up, Giddy?
Wait, okay, so this is just more me being curious.
Oh, you're fine.
How does it actually emit like the full wave? Because in the case of the electric field,
Yep.
Can't have electric potential without an EMF. So like,
well, not necessarily. So again, what's creating the wave in this case is the acceleration of the charges due to the fact that the current is time changing. Right. So in this case, I have dynamics because I have an oscillating source. That oscillating source then creates radiation in this case, which gives me these waves, which then goes to a plane wave out in the far field limit. So basically, that's the same thing as saying if I had a single charged particle in space and I oscillate it up and down, that would also create radiation. because the movement of it would then create a time-changing electric field due to the fact that the electric field is changing as this guy oscillates up and down. But since it's also moving, that creates a current, which means it also creates a magnetic field.
Oh, the axles. Okay.
Okay. It would also happen for a single charged particle, which is accelerating.
Yes.
So if I accelerate that one, it has an electric field by itself, but since it's moving, it's going to have a time-changing electric field. And also, since it's moving, it has a current. And since those are both changing with time because it's accelerating, that would also create radiation. Okay, so we have to have some sort of acceleration to create light. Okay, so the overall net result of all these things is electromagnetic radiation or an electromagnetic wave. I don't want that one. I want the other one. Where are you? I think it's not in this one. Let's go back to here. That's what I want. So this is the result of this. So basically what we get is, as we showed in the beginning of the semester, we get this idea of an electromagnetic wave, where again, we have an oscillating electric field with a magnetic field, which again are in phase with each other. This guy then reaches its maximum at the same time this guy reaches its maximum. The difference is because these guys are out of perpendicular to each other, that means my electric field then is going to oscillate on this axis. Let's call this the y-axis. This one's going to oscillate on this one, which would then be my z-axis, and then my wave is actually propagating in the x direction. Okay, so that's what's happening here. Is this guy is oscillating or moving in the x direction. This guy is then oscillating in a plane perpendicular to the direction of its oscillation, or of its propagation. Sorry. This one then is oscillating at a direction perpendicular to both the direction of propagation and that of the electric field. Right, so this is our result of this guy, my electromagnetic radiation. Okay. Now, typically when people think of magnetic fields oscillating with electric fields, they think of light. Well, this is not the only thing we can actually have. So electromagnetic radiation is actually the entire spectrum of possible frequencies and possible wavelengths. So typically, and like I said, when people think of light, right, or electromagnetic radiation, you think about the lights that come out of here, like white light, different colors. That's only a small section of the entire electromagnetic spectrum. So technically, this thing goes from what? Zero frequency, i.e. very large wavelengths, all the way out to huge frequencies with very, very small wavelengths, right? So the biggest wavelengths, i.e. the smallest frequencies are, in this case, excuse me, what we call the radio waves. Typically, this is going to be more like AM radio down to the FM radios. So we talked about this before, but the reason that cars do not have an AM radio antenna is because the entirety of the car acts like an antenna. Right? So this guy can range anywhere from the size of a building or bigger, the size of the entire Earth, all the way down to roughly about the size of your hand. So this is what we call the, excuse me, the radio wave. Next up, we have the wave or the microwave. This is what your microwaves run off of course. So this is about the size of a hand to about the size of a pinhead. After that, we have the submillimeter, which is the size of a pinhead, down to about the size of the width of a human hair. So that is that frequency range. Then we have the infrared, which is slightly below than the visible light spectrum. So that's about the size of a human hair to about the size of a single cell organism. From there, around that same size is where you have then the visible light. So that's from about 400 nanometers up to about 800 nanometers, about 750 nanometers. After that, we have then ultraviolet. This is what causes mostly skin cancer. Right? So in this case, this is from the size of a single cell organism down to the size of a molecule. From there, we have our X-rays. X-rays are actually kind of cool. The way we create X-rays is you actually cause radiation to come from the cascade of the orbital shells. So in this case, you have an orbital shell, which then drops from, say, the K level down to the D level. In that case, then that creates your X-rays. So it's a cascade in that case. So that happens from the molecule size down to about the atomic size. And then anything higher than the atomic size is what we call gamma rays. So these are your ultra high energy ones that typically come from things like AGNs, where AGN is what's known as an active galactic nuclei, which is outside of our solar system in this case. So these are our stupidly high energetic ones. We kind of talked about this last semester. Each one of these different frequencies corresponds also to a color of light. So meaning that they have a particular temperature associated with them. This is the idea of, again, your infrared thermometers that you use. So for example, we know the surface temperature of the sun is about 5,000 Kelvin based off of the temperature, or sorry, based off the color of the light, right? So this gives us our most probable frequency, which is given off. But again, when we talk about electromagnetic radiation, we're talking about the entirety of the spectrum, not just what we talk about for the visible light spectrum. So it goes all the way from zero frequency out to infinite frequency. The higher the frequency, the more energy that it actually contains. And we're like, okay, too bad. So cool. So let's go back to the text. So we know that light now is a wave. And remember that waves carry both energy and momentum. So let's talk about the energy and momentum that waves actually carry. So electromagnetic waves are waves, obviously. So they carry both energy and momentum. So let's talk about each one of these guys. So how much energy does it carry and how much momentum does it carry? And to do that, instead of actually deriving this, I'm going to try something different this time. I'm going to define a new quantity, which is what's known as the Poynting vector. So the Poynting vector is defined as 1 over mu naught times the electric field crossed by the magnetic field. So let's point out a couple things about this. So we just said a moment ago that if I take my fingers and I point them in the direction of the electric field, i.e. right hand rule number 2, curl towards the direction of the magnetic field, my thumb then will point in the direction of wave propagation. So since this is E cross B, that means this vector, the Poynting vector, is going to point in the direction of wave propagation. So this is the first thing we're going to notice. So this thing then points in the direction of wave propagation. All right, so that's this guy. Now, what else can we find out about this? So first of all, if we take the absolute value of this guy then will be equal to 1 over mu naught times the magnitude of the electric field times the magnitude of the magnetic field times sine of the angle between the two. However, since we're dealing with light, we already said that the electric field and the magnetic field are perpendicular to each other, which means what's the angle between them? 90, what's sine of 90? 1, so this thing is actually going to be then equal to 1 over mu naught times then the electric field times the magnitude of the magnetic field. Okay? Now, let's talk about this quantity a little bit. Now, if I went through dimensional analysis on this, basically meaning if we took all of our units that we know for mu naught, we know for the electric field, and we know for magnetic field, it turns out that this thing has units of the watts per meter squared. So this is actually the units of this guy. So this thing has units of watts per meter squared. Does anybody remember, going back 1,000 years now to when we talked about waves, what has units of watts per meter squared? Anybody remember this? Or let's write it this way. Good, it's power divided by area. So we know a watt per meter squared is a power, which means that is equal to a joule per meter squared per second. Okay? So first of all, let's talk about what this thing actually is. So what this means is what? If I had some sort of area, so let's say this is my cross-sectional area. So this is my area A, and then I have light coming onto this area. Okay. What this thing then tells me then is the amount of energy per meter squared per time, which is deposited onto this area. Who's okay with this? So this thing then represents the amount of energy per time per area. So basically, the magnitude of this thing called the Poynting vector describes how much energy that the light is actually carrying. Okay? So this thing then is a description of the energy carried by the wave. Doing okay with this? Now, going back to when we talked about waves, this thing is the same thing as Gideon just said. This is the power per cross-sectional area, or in this case, more appropriately, the surface area. Anybody remember this from?
Think about sound. Was it sound?
Something about sound. We talked about specifically about sound. So we said this was, the person was standing here. There was some source here. Good. We said that this guy created a spherical wave that moved out. We were talking about this was the amount of sound that this guy heard at this point. It's what? It's the intensity, right? So this guy is actually the intensity. So it turns out that my Poynting vector, at least the magnitude of the Poynting vector, is simply the intensity of the light at a given point. Right? Which again means that it's the amount of energy contained in amount of a cross-sectional area at a given moment of time. Okay? So the magnitude of this guy simply then is the intensity. Okay? Now, one thing to point out is since we're dealing with light, light is going to be oscillating with these huge amounts of frequency, which means that for the most part, we won't see how it changes from moment to moment to moment. What we're going to see is the average of what this thing is actually doing. This is what we're going to call a time average. So in general, what we're going to care about then is the time average of the absolute value or the magnitude of this Poynting vector. So when I write it this way, this is then a time average. Okay. So let's talk about time averages. So in this case, this guy is then going to be equal to the amplitude of the electric field times the amplitude of the magnetic field divided by 2 times mu naught. Now, the reason I know that is because, again, my electric field is proportional to sine of theta. We also know our magnetic field is proportional to sine of theta. So in this case, I'm taking the average of sine squared of theta. Okay with that? So meaning that if I plotted sine squared of theta versus time, this thing is actually doing this. Right? So if the maximum value of this guy is simply 1, what's the average of this? What's the average of sine squared? 0.5, it's half, right? So the average of this guy is simply 1/2. This is where the factor of 1/2 is coming from. So the factor of 1/2 says that since this guy is actually highly oscillatory, and this thing goes as a sine squared, the average of the sine squared then is simply given by 1/2. Okay, so in this case, since we have these highly oscillatory waves, we're not going to see how this changes from moment to moment to moment. All we're going to see is the average value at which this thing is coming through us. Okay. Now from here, we usually define this guy then to be the RMS value of the electric field times the RMS value of the magnetic field divided by mu naught. So what's the RMS value? So the RMS value is the root mean squared of the quantity. So ERMS is equal to the square root of the average of the electric field squared. So this guy works out to be the magnitude of the electric field divided by the square root of 2. So this is the RMS value of the electric field. Simultaneously, the RMS value of the magnetic field is equal to the square root of the time average of the magnetic field squared, which is equal to the amplitude of the magnetic field divided by square root of 2. Okay? So let's use this. Let's do an example, see how this thing actually works. So let's look at this guy. Oh, no, wrong one. Go back. Go back. Thank you. Examples. Let's do this one. I think this is example number 3. Yeah. So this says that radiation from the sun reaches the Earth above the atmosphere at a rate or an intensity of 1,300 watts per meter squared. Says assume that this thing is monochromatic light, which means that it's a single frequency, and calculate the magnitude of the values of, this should be the amplitude of the electric field and the amplitude of the magnetic field. Okay, so let's draw our picture here. So here's the surface of the Earth. Okay, here's our atmosphere, top portion here. We have some wave coming in, like this, from the sun, and it tells me that the intensity at this point is 350 watts per meter squared. From this information, we want to know what is the amplitude of the electric field as well as the amplitude of the magnetic field. So these are the 2 things that we want to know. So what do we know? We now know that the intensity is equal to the time average of the magnitude of the Poynting vector, which is the same thing as the amplitude of the electric field times the amplitude of the magnetic field divided by twice of mu naught. Okay? Now, from here, we have what? 2 unknowns with 1 equation. We can't solve that, right? But what we do know is that going back to the speed of light is 1 over the square root of mu naught times epsilon naught. But if we use our analogy with velocity selectors as well as the Hall effect, what we always found was that the velocity was equal to the ratio of the electric field to the magnetic field. Okay. This is also true here. In this case, the speed of light is also equal to the amplitude of the electric field divided by the amplitude of the magnetic field, because they both carry a sine term, which are just going to cancel out. Bless you. So now we have 2 equations because we know the speed of light, that's 3 times 10 to the 8th meters per second. So we can use this guy now to eliminate either the electric field or the magnetic field, and then use that into here to write this guy as either the electric field squared or the magnetic field squared. Pick your poison, doesn't really matter. Okay. So, pick on you. Which one do you want to solve for in that case? You want E0 or B0? B0, so let's solve for B0. So B0 in this case, according to this guy, God, this chunk sucks. So B0 is then going to be equal to what? The amplitude of the electric field divided by the speed of light. Okay? Now, let's plug that in here. So now I'm going to get an E0 divided by 2 mu naught times B0, which is then E0 divided by the speed of light. So this guy then is going to be what? E0 squared divided by 2 times mu naught times the speed of light. So from this, now we can actually solve, because we can solve for the electric field. So let's do that. So over here, we're going to get our electric field then. Amplitude is equal to the square root of 2 times c times mu naught times the intensity. Plug that in. What we're going to get in this case then is, according to this, 1.01 times 10 to the 3rd. And this is an electric field, so that has units of newtons per coulomb. We doing okay? Now, since we know that, we can simply plug that back into this expression. We're going to take this guy, divide by the speed of light, which is, again, 3 times 10 to the 8th. So plug that guy in here, we get, according to this, 3.37 times 10 to the minus 6th. Okay? So that's it. So what always is going to be true is that the electric field will always be much bigger than the magnetic field, because it's related by a factor of the speed of light. So the amplitude of the electric field will always be at least 3 times 10 to the 8th times bigger than that of the magnetic field. Okay? So tomorrow we'll talk about momentum, how much momentum is actually carried inside of the wave. And then that's going to bring us back to forces. And then we'll go back to forces tomorrow, which means we're going to have to draw 3 body diagrams. What's that? What's what? So mu naught is the permittivity of free space. So that is 4 times pi times 10 to the minus 7. So what's this guy? Yes, I know it's a shadow. Okay. What's that?
This like this.
Yep.
So the magnetic field and electric, because it has to be dynamic, it's always time dependent.
Always has to be time dependent.
It can also be air dependent.
I mean, it could be.
It can be both.
It can be both. But to generate light,